Alright, there have been some requests for a video tutorial for the archetyper package, so I thought I'd put a quick one together here. So we'll get started. So we'll first install the archetyper package, or load the archetyper package, and we'll see that on the there are two methods or functions available within archetyper. The first is a generate statement that will spin up a starting project with all the files and directories that you might need for the data mining or data science pipeline. The other is a generate demo, which generates the same files and directories, but they're just complete with a runnable code base for an example project. So I'll start with the demo project here and just run that. Oh, and you'll see here that it's telling me that it did create that, but it created it in a temp directory. So let's give it a path where we want this to be stored. So let's do this, and then let's add it to this training folder. Alright, so now we can see that a project was created in the training directory that I have on my desktop, and that demo project is called Hospital Readmissions Demo, and the project basically builds a not so great model to predict hospital readmissions based off the publicly reported complications and other structural characteristics of the hospital. So not a particularly useful project, but it's good for just demonstrating the archetyper project. So let's kind of crack open the project here and see what's inside. So first thing you'll see is a number of directories for storing data, docs, models in our R code. And we'll also see a getignore file, a readme file, and then some project metadata in the rproj file. So I'm going to go ahead and open the readmissions demo here, and to do that we just click on the rproj file. And we don't need to save this. So it's going to open the project within the context of the hospital readmissions demo. Alright, so before I, well, first I'll just look at the R code too. So if we click on the R directory, we'll see that there's all the R code's been stored sort of logically separated from the other files. So I'm going to hop on over to the GitHub page. This is a site built with package down, and you can see how we create a project and everything here. But I really wanted to go here to point out this image, and if we zoom in here, we can see sort of a visual grouping of the files and directories that are created through archetyper. So we'll see that we have dedicated files for each functional component. So there's sort of layers of isolation between each component here, and each one of these can be run separately with no dependency on the running the step before it. So once we run integrate, we can run enrich as many times as we want without having to rerun integrate. And the same is true with model and evaluate. And that way, if you have particularly time-consuming work that happens in any of these phases, the design is to persist the result from each stage into a directory of some sort, and then make use of that in the following directory or in the following component. And that's all orchestrated through this mediator script, which is really responsible for executing the code in linear order from beginning to end. So it kind of is in charge of the whole pipeline. We'll also see a common.r file, and that is where we store shared libraries, sort of common variables across the project. There's a logger that gets initialized there, and we also store other important information that might be common across the project, like maybe smaller functions or something like that. The common.r is sourced by each component or each step in the pipeline, so that anything that's in common is available to all these steps along the way. And then likewise, utilities is sourced by common. So if we have common functions that we want to make available to all components, once each of these components sources common, they'll also get access to any utilities that are available here. We also created a file for exploration, so sort of transient data analysis to see what features we might need to develop, or just sort of the data exploration part of the process. That's not part necessarily of the linear pipeline, but a necessary step nonetheless. There are also directories for storing input data, data that's sort of in flight or working data, and then output data. So as the process runs, we'll make use of these directories for different to store data at different phases in the pipeline. And then output data is stored in the docs directory. And this is, and we'll see in the example here that we're using our markdown document, and when the mediator runs the whole pipeline, it also generates this markdown document and stores it in the docs directory. There's also a working API in the demo, and it makes use of the model that gets trained along the way, so that you can pass in a record through the RESTful API and get results back. So the goal is to give an example of what an end-to-end data science pipeline might look like, with sort of an example of how each logical component can be used. There are a number of other files that get generated. I mentioned our project before. This is important to store project metadata, but it also helps identify the home directory for relative paths. So the project encourages the use of relative directories using the here package rather than using set working directory, which if you've been doing R for any time, you'll notice that where setting your working directory is kind of a pain point. So we certainly encourage the use of relative directories. Unit testing and integration testing can be done in the test.r package using the test.that library. In the test.r file using the test.that library. So it has an example unit test in there, and this file is executed in the mediator before the whole pipeline runs. So before your pipeline runs if any of your unit tests or integration tests are failing. There's a gitignore file. This comes pre-populated with commonly excluded files from source control. It uses the gitignore package to generate the gitignore file. So that's very helpful, so you don't have to remember all the files that you typically exclude from a project. There's also a README file, and this has some scaffolding in there so that you can give quick introduction into what your code does and how to run it and who to contact if you need to contribute to it and so on. If you're using databases, there's some other configurations or arguments that the generate command accepts, whether you're using JDBC or ODBC. And if you're using JDBC, for example, it will generate this config.yaml file to store database credentials and other secret information. So you could have a dev, QA, and a prod database, for example, that you might point to. And this YAML file is excluded from the gitignore file so that that secret information isn't committed to source control. I should also mention that if you run the project with a JDBC or ODBC configuration, the integrate.r file has an example of a database connection that gets generated in that configuration. And finally, there's a DML/DDL.SQL, which DML standing for, of course, data manipulation language, and DDL standing for data definition language. So if you're building some data up front within your database, like tables or views, or maybe reading some insert statements, whatever that might be, it's good to store them in a SQL file and keep them packaged up with your code so that as you change your R code and your SQL code side by side, they're maintained, there's parity maintained between the two, and they're stored in the same place. All right, so that was sort of a mouthful. Let's go back over to the R code. All right, so again, whether you run the project with generate or generate demo, this will all look the same. The only difference is that you'll see in generate demo, an actual project that's been developed. And again, this project was developed just for demonstration purposes. It's not a production or publish-worthy model by any stretch of the imagination. So, so in this case, I'm using I'm sourcing some data, some public data from Centers for Medicare and Medicaid Services, and its hospital data that's published quarterly. So it's going to read in some raw data, and the goal here in the integration step is to pull data from different data sources, join it, standardize the data types, and produce a 2x2 tibble or data frame with observations as rows and features as columns. And since this is really a data integration task, we're not really doing feature engineering here. We're really just preparing the data in a standardized way that is common across models that we might build. So this is stored in a feather format, which is a sort of a compressed format that allows R or Python to interpret a data frame, and it also stores all the metadata of the data frame along with it. So the feather format's it's a great file format if you're not familiar with it. So we're storing the 2x2 data frame with observations as rows and candidate features as columns into the data working directory. Okay, so once we've done the integration step, we will enrich that data. So here you can see that we're reading in the data from the working directory, the integrated data, and then we're going to start doing our feature engineering. So maybe we're standardizing some of the text, we're creating factors, we're maybe doing some kind of log transformation if the data is rightward skewed, and maybe we account for some other, for NAs, we might want to stub that out for an unknown or something like that. Here we're also imputing the data, so I'm using predictive mean matching using the mice package, and that will iteratively predict missing values using all the other features as predictors to have a more tailored estimate of missing data. Of course, beware of the dangers with imputation and do your homework there on when it's okay to impute and when it's not. Here we're also removing outliers. I'm using Cook's distance as a method for removing outliers. You can use z-score based methods or isolation trees or whatever you might want to use there, but Cook's distance is a nice measure for outliers in that it looks across all features to find outliers holistically. Here I'm centering and scaling some of the numeric data, and then removing some highly correlated features, and then finally assigning testing and training partitions to the data. So we've read in the integrated data set, and now we're producing an enriched data set that has been tailored for the model that we are training. If we were building something like an XGBoost, maybe we wouldn't need to account for abnormal distributions, since tree-based models are entropy-based and don't use, or it's not necessary to scale that data. So this important part of this step is that we're doing transformation specific to the model that we're training. All right, in the modeling step, we are training we're just doing a linear regression, and then we're going to build a stepwise model, as a secondary step based off the AIC. So we're reading in just the training partition. So here we're filtering on the training indicator. And then we're building a model, and then again making that a stepwise model, and we're going to write out using the Broom package all the coefficients to a data frame, the model performance, and the model itself we're going to store into a models directory. So we can see that's happening here. All right, so the model's been built, and I'll run all this at the end just for the grand finale. The next step is evaluate. So we'll read in just the testing partition. So So we're filtering where it's not the training indicator. So this is just getting the testing data, and we're also reading in the model that we just saved, and we're going to apply that testing data to the apply that model to the testing data and get an updated testing data set. And then we'll write that out to a data output directory, and we can also store some metrics here based off the overall performance of the model against the training data set. Okay, and notice that at each step we're persisting the results to a directory, and that allows us to have a snapshot of the data each along the way, and it keeps us from having to reprocess especially computationally intensive data. Each time we run our process, we can sort of inch forward each step with a persisted result at each step. Next, we have the presentation layer or component, and this will make use of all the data that we stored in the data directories, and we'll read that in and produce a file or a PDF that is sort of a summary of our analysis. And this is dynamic, so as we make changes to our model, our generated report through our markdown will be updated. And we could of course make this produce a HTML document or slides or something like that if we wanted to. All right, there's some testing here, so we can see that there's a test. We're using test that. So here I'm just giving an example test that tests the rounding of the pi function, and that does work, as we'll see. I'll point out briefly the common library. So this is what all of those components source. So we can see that they're using one logger. Maybe we're setting a scientific penalty so that we don't see the notation up to a certain decimal. Here the project name is assigned to a variable if we want to make use of that in the file name, for example, that we generate. And then we have a number of packages used. Briefly, the tidyverse, self-explanatory for anyone that's been doing R for a while. Snake case I use to standardize column names as I'm pulling in data. And you'll see an example of that in the project. Feather is to support the feather formats that we're storing. Config is if we're using JDBC connections, and that allows us to store data externally in a YAML file and read that in using the config package. I'm also using log4r for making comments across the or making logging to do logging at various levels across the project. So we could say, on a log with a warning at this point, or just information at this other point. The banner commenter, it's not actually used in the project, but I do include it because I like the ability to generate comments that are formatted. So if we look at any comment in the project, all of these are generated with banner commenter, and it makes a very nice formatted comment. And then we're using the here package to maintain relative directories. I'll also point out the mediator package. This is responsible for executing each step in linear order. So you can see we log what we're doing, and then we actually call that file. Each of these is wrapped in a try-catch, so that if something happens along the way, the whole thing fails and it won't continue running the pipeline. Excuse me. When we get to the markdown process, we call them render function, and it will store the created markdown document, or the output document, into the docs directory. Okay. A couple sort of miscellaneous items. There is a lint file, so if we want to test if the formatting of our code or the style of our code, we can run this for each component. So, I'll run this for integrate just as an example. So I'm a big offender of using more than 80 characters. So you can see that it's telling me that I have a lot of lines that are 80 characters or more for this integrate file. But it will also tell you if you have spacing issues or your brackets are in the wrong place, or so various things like that are helpful. So that's linting, and I think that, and then we finally have the API itself. So here's an example API using the model that we just created, or that was created. And I also provide an example request so that when we spin this project up, you can just uncomment this and add that in as the request body, and then you can see an example of what those, how to call the predict API and what those results will look like. Alright, so I think that's pretty good. I'll just quickly point out the markdown file, the getignore file that gets generated and how it excludes the database credentials. And I'll also point out the README file that gets generated with just sort of some scaffolding. All right, so with all that being said, we'll sort of have the grand finale here. So we'll close some of this stuff down, and we will run the mediator top to bottom, and that will really kick off our whole pipeline. So here we go. And yep. All right. Oops. Okay, we'll just run this whole thing. So it's running our tests. We can see that our tests passed, and then it's gathering and integrating data. I'm going to pause this here because it pulls in quite a bit of data from using a curl command. Okay, so that's been loaded. Now you can see that it's on the enrichment step, so it's imputing data. So this PSI stands for Patient Safety Indicators. So it's imputing some missing data there. Here we can see that it's running the actual model, and let me scroll back up. So and then it reran that model using this stepwise AIC model, and then the results are stored, and we get an output created in the docs directory. So let's look at what happened once we ran all that. So let's first look at this document that was generated. So this was created at 5:40 p.m. So this just happened. And this is a document predicting hospital readmissions by a guy with a very interesting name, readmission. There's some lorem ipsum here just to make it look real. And then here the actual coefficients of each of the predictors is stored here. So this is all generated from the model that we just trained. It also provides the predictors with the estimate values, or the coefficients for the upper and lower confidence intervals. I'm sorry, I misstated earlier. This first table is just profiling our data. So we see our average value in upper and lower bounds, and then we have the coefficients in this other table with their p-value and test statistic and all that good stuff. We also have model performance here, so we can see the R-squared and adjusted R-squared for volume, and so on. And then I just put a little bivariate scatter plot here to show some with a AB line between the predictors and the actuals. So this is just sort of a dummy project, but you can kind of see how a whole document can be generated through the pipeline. I'll also point out that the data was created along the way here. So there was no input data since we called that with curl commands and pulled it from another repo. But you can see, in the working directory, there's an integrated file that's version controlled. So that's the result of the integration step. There's an enriched file that gets generated using from the enrich step. And there's output data that has our performance statistics and data that with the appended predicted values, attached. Notice that everything in the output file I put in CSV because this is data that we might share with others. But in the data working, I store everything as a feather file just for saving space. And the model has also been trained, so we'll see, that a new model was created on this date. So that is an example of an end-to-end model. And if you have questions or if you have comments or something's not working for you, feel free to go to the Git repo page and you can report a bug over at the top here. So welcome any comments that you might have. So thanks everyone, and appreciate your listening.